Hi everyone, welcome back to another video on Oxbridge and Imperial Engineering, Natural Sciences and Mathematics interview practice session, study session. Today we're going to look at another problem called the garden hose problem, and I'll be going through this problem with you. I haven't seen this problem before, so I'm going to work through this problem step by step. And hopefully along the way you can also learn about the ways of problem solving, or the art of problem solving, as a lot of people call it. So let's get started. The question says, I want a jet of water to exit my hose at 24 meters per second. The water enters the hose at a constant rate of 6 meters per second through a circular aperture with radius 1 centimeter. I can control the speed at which the water leaves the hose by adjusting the size of the circular aperture through which the water exits the hose. What radius should the exit aperture have? So what you have here is basically a hose as such, and you want a jet of water to exit the hose at 24 meters per second. So the water leaves at 24 meters per second. The water enters the hose at 6 meters per second. So we want to, I think that by a qualitative analysis, you want the radius of the hose to be smaller so that water gets pushed more at a higher pressure and thereby having a greater velocity. And says it's circular, so let's imagine it's a circular hose, and the aperture is 1 centimeter, and this one would be r centimeters. And you're asked, I can control the speed at which the water leaves the hose by adjusting the size of the circular aperture through which the water exits the hose. So what radius should the exit aperture have? So this is a question about pressure, I believe, and specifically how you can change the area, the aperture, to affect the exit velocity of water. So let's relate everything to pressure, right? So let's say this is P1 and this is P2, and by definition, P1 must be equal to P2 because the pressure within the hose must be the same, must be constant. And we know from the definition of pressure is equal to the force divided by the cross-sectional area. And we know that the force, what we don't know about force is we're only given the velocity of water that's flowing through. But what we don't actually know is the force of that water, because it's normally, if you think about the constant velocity in Newtonian mechanics, things that have the same velocity has zero acceleration and therefore zero force. But I think in this case it's a bit different. The situation is a bit different. Because there is actually a change in the velocities of the water as it goes through the pipe. So there is actually a change in the velocity. But let's just go back to this scenario here in the initial state. So of 6 meters per second going through the pipe. And what this means is in 1 second, water moves 6 meters into the pipe. And okay, so in 1 second, I have an intuition here actually. My intuition is that the velocity times the area v1 a1 must be equal to v2 a2. This is my intuition, but let's just think about it for a second. Let's do dimensional analysis, let's say, and see if v times the velocity times the area is actually the pressure. Let's relate the pressure together. So we know that pressure is equal to force divided by area, and in dimensional analysis, force is equal to mass times the acceleration, and area is meters squared. So the unit for pressure is gonna be in the form of kilograms per meter per second squared. And what we're given here is V and R. So we're going to say that the unit for pressure is going to be equal to the unit of velocity to the power of alpha times the unit of radius to the power of beta. And we know that the unit of velocity is meters per second, so meters per second to the power of alpha, and the unit for radius is meters to the power of beta. And cleaning up, we get meters to the power of alpha plus beta times the seconds to the power of minus alpha. We have omitted a few constants here. And I think one of the most important constants that we've omitted is the density of water. So let's put that in to the power of gamma. So density is kilograms per cubic meter to the power of gamma. And so you get kilograms to the power of gamma times meters to the power of alpha plus beta minus 3 gamma, and times seconds to the power of minus alpha. And equating those two expressions, you get gamma is equal to 1 and alpha is equal to 2. So therefore, alpha plus beta minus 3 gamma would be equal to 2 plus beta minus 3. And this must be equal to minus 1. So 2 minus 3 is minus 1. So beta must be equal to 0. And this is quite surprising. If beta is equal to 0, oh no, okay. So dimensional analysis would not hold under these circumstances. If dimensional analysis doesn't work, let's try something else. So let's try the flow equation. So essentially, you want to equate the pressure in the initial state and pressure of the final state. And you know that the pressure is equal to force divided by area. That's the most fundamental definition of pressure. Okay, let's hold a second. Let's not use this equation. Let's think about what you'd. I'm going to think about what the product of velocity and area actually mean. So velocity is, the pressure doesn't have to be equal, but the flow rate must be equal. So flow rate must be equal. This is the crux of solving the problem. the flow rate must be equal. And the flow rate is the rate of change of volume, because the rate of change of volume initially must equal to the rate of change of volume in its final state. And the flow rate is equal to AV, because the velocity is the meters, the rate of change in the progression of the water in the hose, whereas the area times the velocity, you'd get the rate of change of volume. And so having V1 times A1 equaling to V2 times A2, you can get essentially that R squared is equal to V1 times 1, because it's 1 squared divided by V2 is R squared. So R squared, substituting in the values, we have 6 divided by 24. So R would be, which is equal to 1/4, so R would be equal to half. So radius is equal to a half in this question. So we have radius is equal to a half. Now I'm going to check the answer and see if it is correct. And it is correct.